We're going to start off our session number 8 with a game of darts. You can see we have a dartboard here and I'm going to play a game of darts. The entry fee to play this game is 30 rupees. So the moment I start playing, I need to pay 30 rupees. And in 30 rupees, I am allowed a maximum of 15 tries. You can see this red dart on the bullseye. Every time I hit the bullseye, I get 4 rupees. And every time my throw misses the bullseye, I lose 3 rupees. So let's repeat. I'm playing a game of darts for which the entry fee is 30 rupees. I've already spent 30 rupees. In 30 rupees, I'm allowed a maximum of 15 tries. If I hit the bullseye, I get 4 rupees. And if I miss the bullseye, I lose 3 rupees. And I don't miss the bullseye more than 3 times. The maximum number of times that I will miss the bullseye will be 3. So the question here is, what is the minimum number of times I should hit the bullseye so that I don't end up with a loss? You figure this one out while we go through the concepts in the 8th session, which is based on inequations, and then we'll see how to solve this. Let's play this game. You figure this one out while we go through our session number 8, which is on inequations, and at the end of it, you will understand the solution to this game of darts. You figure this one out while we go through our session number 8, which is on inequations. By the end of this session, you will get the answer to this game of darts. We've already studied 2 chapters of equations. We've gone through a session on linear equations and another one on higher order equations. Now in equations, what we learned is that there is a left hand side, there is a right hand side, which is connected by an equal to sign. In this chapter of inequations, there will be a left hand side and there will be a right hand side, but what connects these two is not an equal to sign, it will be something else. Now what else can it be? It can be a less than sign, it can be a greater than sign, it can be a less than or equal to, it can be a greater than or equal to. So whenever you have in an expression or in a full statement 2 sides which are connected by either a less than or a greater than or less than equal to, greater than equal to, this would be a problem of inequations. Now let's understand a few properties of inequations. Suppose we are given x is greater than y, and then we add the same term a on both sides. What can we say about the inequation? Now if you are going to add the same term a on both sides where originally x is greater than y, then the new expression, new term that we get, x plus a and y plus a, we can definitely say that x plus a will be greater than y plus a. Similarly, if we subtract the same term a on both sides, once again we can definitely say that x minus a will still be greater than y minus a. What happens when we multiply the same term a on both sides? Can we once again definitely say that ax will be greater than ay? We can't do that anymore, because now the answer depends on whether the term a is a positive number or a negative number. If it's a positive number, then we can definitely say that ax is greater than ay. However, if a is a negative number, then ax will become less than ay. So here we cannot be sure of what is going to happen. Similarly, if we divide x by a and we divide y by a, the situation would be similar to the previous case where we can't say for sure. Reason being, my answer would again depend on the sign of a. And to go back to x greater than y, if I simply take the reciprocal of x and y, what can I say? Can I say 1 upon x will be definitely less than 1 upon y? That's one of the most common answers that we get. However, here also I cannot generalize. I would still say it depends on the sign of x and y. And if you are still struggling to figure out why, you need to understand that when x is greater than y, it is possible that x is positive and y is negative. In which case 1 upon x will still be a positive term, 1 upon y will be a negative term. and 1 upon x will remain greater than 1 upon y if to start with x was positive and y was negative. If you try to fit in examples where both x and y are of the same sign, then you will over and over again prove it to yourself that 1 upon x will always be less than 1 upon y. But don't miss out this possibility where x is positive and y is negative. Let's move on to quadratic inequations, and let's try and understand quadratic inequations with some examples. Suppose we have a quadratic inequation which says x square minus 7x plus 12 is less than 0. We can factorize this and say x minus 3 into x minus 4 is less than 0. What this means is product of two terms is negative, and that happens only when one term is negative and the other is positive. So we can have a case where x minus 3 is negative and x minus 4 is positive, or we can have a case where x minus 3 is positive and x minus 4 is negative. Now if we continue along these lines, then we will get x is less than 3 and x is greater than 4. Now it is impossible for a number to be less than 3 and at the same time be greater than 4. So this is ruled out. Another possibility, as we have seen earlier, is x is greater than 3 and x is less than 4. This means that x has to lie between 3 and 4, and hence this can be finally summarized as 3 less than x less than 4, which would be the final solution for this quadratic inequation. As we studied in the earlier examples involving modulus, where we said that whenever the inequality is less than, the answer would be a closed range, we once again find this true for quadratic inequations. The inequality was less than, and we have found the answer, the final solution, to be a closed range. After seeing an example of an inequality which was less than, let's now understand what happens if you have the same example, x square minus 7x plus 12 with a greater than inequality. Once again, factorizing this, we get x minus 3 into x minus 4 is greater than 0. What this means is that product of two terms is positive, which can happen when both are negative, which means x minus 3 and x minus 4 both will be negative, or it can happen when x minus 3 and x minus 4 both are positive. In either of these two cases, the product will be a positive number. If we solve this, we get x is less than 3 and x is less than 4, or if we solve this, we get x is greater than 3 and x is greater than 4. Now if x is less than two different numbers, as in this case we notice x is less than 3 and x is less than 4, then it will always be lesser than the smaller of the two numbers, and hence we can consolidate this and say that x is less than 3. On the other hand, if x is greater than two different numbers, then x will always be greater than the larger of the two numbers, and hence we say x is greater than 4. As we had learned earlier in inequations and modulus, when the inequation is greater than, x lies beyond these two roots, and hence it gives us an open-ended range. So another way of learning quadratic inequations, when the inequality is a less than inequality, you solve the equation as a quadratic equation and then put x lying within the two possible roots. So for less than inequality, x lies within the roots. Whereas for a greater than inequality, if we had solved this as a quadratic equation, the roots would have been 3 and 4. And because it is greater than inequality, x would lie beyond the roots, which would mean greater than 4 or less than 3. This is how we can solve quadratic inequations based questions using shortcuts. Let's now move on to higher order inequations. Here we can look at an example which is an inequation of degree 5, because there are 5 brackets each involving x. We want the product of all these 5 brackets to be a positive number. When would that happen? That would happen when all the brackets are positives, or when an even number of brackets would be negative, so that the product of these negative brackets would eventually turn out to be a positive number. So that's one way of looking at it and trying to identify values. Let's try and solve this using a graphical method. So suppose I look at a number line and then I plot these points. Suppose I have 2 and then I have 5, 7, 10, and then we look at 15. When I look at these points plotted on the number line, I can take a value in any of these ranges, which means I can take a value, say, greater than 15. So if I extend this line, if the value of x is greater than 15, I definitely know all the brackets are going to be positive, and hence for x greater than 15, this inequation will always be true. So I put a tick mark which indicates that in this range the inequation is always satisfied. After that, I mechanically need to alternately put crosses and ticks, and that is my solution. Which simply means that if x lies between 10 and 15, then I definitely know this inequation is not going to be satisfied. But for x between 7 and 10, this is going to be satisfied. So the fastest way of solving such questions is draw the number line, plot these points 2, 5, 7, 10 and 15. Take any one range. We started off with more than 15. If x is more than 15, this would be satisfied. So we put a tick mark, and then we moved on and alternately put down ticks and crosses. So here my solution would be x lying between 2 and 5, x lying between 7 and 10, and x being greater than 15. This would be the solution for this particular question. We're now going to move on to questions which pertain to finding a common range. We have these 3 inequations listed out here, and we need to find a common range for x which would satisfy all the 3 inequations. Each inequation would have its own range, but our answer would be that common range which would satisfy all of them. So let's try and solve them one at a time. Suppose we look at this first inequation, which is mod x minus 2 greater than or equal to 5. Going back to our earlier concept, it means distance of x from 2 is greater than or equal to 5. So suppose I plot point 2 here, then we are looking at distance from 2 being more than or equal to 5. So when I take 5 more on this side, I come to a point 7, and when I take 5 on this side, I come to a point minus 3. Since x, the distance of x from point 2 has to be more than or equal to 5, it can be equal to 7, it can be equal to minus 3, and it can also be anything more than this or less than this. So when I talk about the range for x, for this inequation, our range would be x greater than or equal to 7, x less than or equal to minus 3. Let's now move on to the second inequation, which has these 4 brackets involving x. Hence it is an inequation of degree 4. And let's plot these points. We have a point which is minus 6 to start with, and then we have a point 3 out here, and then we have a point 7 out here, and then we have point 11. So we have plotted these 4 points on the number line, and now we go back to the method that we learned some time back. If x is more than 11, every bracket here is going to be a positive number, and hence the overall product is also going to be a positive number, which means the inequation is not satisfied if x is greater than 11, so we put a cross, and hence we move to the left by alternately putting a tick and a cross. So if I look at this inequation of degree 4, my solution would be x between -6 and 3 and x between 7 and 11. We are not writing that down just now because we are still looking for a common range. So here the range would be 7 to 11 and -6 to 3. This would be the range for the second inequation. If we move on to a third one, which is a quadratic inequation, and if we try to solve this as a quadratic equation, the roots would be 10 and -3. And as we learned earlier, for quadratic inequation, if the inequation is less than, then x would lie within the roots. My roots are 10 and -3, so if I plot the point -3 here and if I plot the point 10 here, then since the quadratic inequation is a less than, x will lie within the roots, and since it was a less than or equal to, x can also be equal to 10 or -3. Now to consolidate, if we are looking for a common range, when I look at my first graph, which was pertaining to the first inequation, x can be less than or equal to -3, which is also common to the second graph, but the only common part with respect to the third graph is x is equal to -3. So one common point that we have through these three graphs is x can be equal to -3, and when x is equal to -3, it satisfies all the three inequations. If I move beyond the point -3 now, my first graph straight away goes to greater than or equal to 7. Hence the other two graphs up to the point 7 become irrelevant because you wouldn't have a common range for all the three graphs here. Let's now look at x greater than or equal to -7. When I look at the second graph, x cannot be equal to 7, it can only be greater than 7. And x greater than 7 up to 10 is also common with the first and the third graph. And hence now when I look at the three graphs, and if I have to look at a common range, then x can be greater than 7, or it can be anything up to 10, 10 included, because 10, the value 10 is common to all the three graphs, and hence the second common range that I get is 7 less than x less than or equal to 10. So when I look at the graphs, after drawing the graphs, and when I look at the common range, my final solution would be x is equal to -3 or 7 less than x less than or equal to 10. This is how this question pertaining to common range can be solved using a graphical method of just drawing the ranges and then identifying the common range. So we go back to our example that we had started off with. We are playing a game of darts, and just to give you a recap, to play the game I have already spent 30 rupees. I am allowed a maximum of 15 tries. Every time I hit the bullseye, I get 4 rupees, and every time I miss the bullseye, I lose 3 rupees, and the maximum number of times that I'm going to miss the bullseye is 3. So how would we solve this? Using inequations. If h indicates the number of times I hit the bullseye, and if m indicates the number of times I miss the bullseye, then h plus m is less than or equal to 15 because I am allowed a maximum of 15 tries. M is less than or equal to 3 because I will miss the bullseye only a maximum of 3 times. And the third inequation is 4h minus 3m should be greater than or equal to 30 because I want to figure out the minimum number of times I should hit the bullseye so that I don't make a loss, I recover my 30 rupees that I have spent. Now if I want to find the minimum number of times that I should hit the bullseye, let's take a worst possible case that I have missed the bullseye a maximum number of times, which is thrice, which would mean 4h minus 9 is greater than or equal to 30, and hence 4h is greater than or equal to 39. If I try to solve this simple inequation, the value of h, minimum value of h, has to be 10 so that I will always recover my money, which basically means even if I miss the target, the bullseye thrice, as long as I cover that up by hitting the bullseye minimum of 10 times, I will always recover my money and will not make a loss. So you can see how this concept of inequations can be used to solve this problem, and maybe you can use this to figure out a winning formula when you visit the casino next time.